Hello everyone, I'm Marco Nardello and I will talk about my work on stray light analysis for a beam alignment system on the LISA optical bench. To have the correct superimposition of the RX and TX beam on LISA is a difficult task, made it even more difficult by the distance between the two spacecraft and the fact that they will move their relative position during its orbit. So it was foreseen on LISA a two-element mechanism to adjust the position of the TX beam. This two-element mechanism is composed by an active aperture mechanism, which is a movable clips that will allow TX beam translation, coupled with a point head angle mechanism, which is a rotating mirror which will be responsible for TX tilting. But the University of Glasgow and the UK Astronomy Technology Centre proposed a different approach composed by four transmitting elements, two prisms in our Rinay Scanner and two parallel plates. These four elements will absolve both the AAM and the PAAM functions, and they will do so with a singular type of mechanism, which will implement all the mechanized function on LISA's optical bench. And this will simplify the research and the choice for the supplier. The adoption of this system is still under discussion, but already some analyses on stray light by my part were made to see their feasibility. So let's go into describe a bit this system. It will be composed, as I said, by two prisms for tilt adjustment of the TX beam. And those two prisms will be independently rotating around their axis, and they will provide the tilting of the beam up to 650 microradians. And the other part of the system is composed by two plates for position adjustments of the beam. These plates will be independently rotating around the optical axis this time, and they will provide translation up to 92 micrometers. Here is a drawing of the whole system. At first there will be a fixed stop, then the Rinay scanner, and then the two plates for beam displacement. In the table we have all the dimensions of the element and positions that were chosen as to give the correct tilt and displacement range for LISA system. The adoption of four elements could create some stray light on the interferometer, and so I tried to investigate the ghosts and the scattering created by this mechanism. And I tried to find every possible stray light path and to investigate the amount of power reaching the interferometer and also the CIS. To do so, a simplifying design was created, and this optical design was implemented in Fred software to find stray light powers. Here is the picture of the optical designs. Not every element in the LISA optical bench is shown, but just the elements present on those that are foreseen to be the main scattering path to the interferometer and the CAS. Those paths are essentially two. The first is to the right of the four elements of the optical system, through the telescope, and then with back scattering towards the RX stop. The other path is backwards through the fiber injector, where there is a reflection, and then in the end the light will enter the interferometer pupil. Here are the optical parameters used for the work. We adopted an incident power on the first surface of the four-element system of 1.57 watt. Each surface was accorded a reflection of 0.5%, and we analyzed scatter due to roughness for roughness of 0.5 and 1.5 nanometer, and also scatter due to contamination for two contamination level of 300 and 600. The amount of power was calculated for two positions in the system at the RX stop with two different field of view, the one of the interferometer, which is 1 milliradians, and one of the CAS, which is 30 milliradians. And the field of view at the pupil for the local interferometer is of 2 milliradians. Backscattering from the telescope was modeled at first as a simple reflection, but then for scattering we saw that a better estimation was needed, and so that's what we adopted. But I will talk in more detail about that later. Since these four elements will be rotating around their axis or the optical axis, according to their rotation, they could lead to different stray light results. So I calculated stray lights for 9 different orientations of these elements, orientation that corresponded to important beam position and tilt. Positions and tilt that are reported in this table. I can already say that I didn't find relevant changes according with changes in position. So in the next slides I reported only results calculated in configuration 1A, that is the first line of the table. First part of the work was analysis on ghosts. I directly reported the stray light power found, which are in every case 1 to the minus 14 is the maximum I found. And some consideration, the main ghost paths are the one due to double reflection inside a single element, like is shown in this picture. This is an effect that cannot be avoided changing positions or putting bit bump, but since the number are small, this will not lead to problems, and we consider these values we found to be negligible. Also, the amount of light reaching the interferometric pupil is much lower than the others, because when we have a reflection from the fiber injector, we have a strong divergence in the beam, so all the power is dissipated of not important paths. Then I passed to studying the scattering. At first we use to model backscattering from a telescope a simple reflection, putting at the telescope position a simple mirror with reflectivity 1 to the minus 7, which corresponds to calculated backscattering from the telescope. But this will give us the wrong angular distribution, because the backscattering does not have the same angular distribution as a simple reflection, and that could lead an underestimation. So in the end we prefer to adopt a two-step approach. So with the with the optical system I showed before, I calculated the stray light from the 4 elements reaching the telescope, and then with a second optical design, I calculated stray light generated in the telescope and reaching the RX stop and interferometer. And then I combined the results of the 2 contributions, multiplying them to calculate the final power on the interferometer. This could lead an overestimation, because not all light entering the telescope from the AAM and C will be rightly coupled to give backscattering, but it's good to have a higher boundary for our analysis. Here I show you the results of this analysis. As I said before, scattering is calculated both for roughness of the AMC surfaces, shown in the first table. Roughnesses are 0.5 and 1.5 nanometer, and also for different level of contamination from 100 to 600 CL. Scattering from the telescope instead is calculated according to two configurations. We consider only contamination, since it's the biggest contribution, and in the first configuration we consider a realistic scenario in which the internal mirrors M3 and M4 are cleaner, they have a CL of 300, than the external mirror M1 and M2 that have a CL of 600. In the configuration number 2, instead, we show a worst case scenario in which we have scattering from contamination of level 600 from all 4 mirrors. So the results from the worst case scenario is that we have 1.1 nanowatt at the interferometer and 0.2 microwatt at the CAS. Concerning the CAS, we can say that this power value is 30 times lower than the stray light coming directly from the telescope, and so it's not a worry. And for the interferometer, we can say that the phase noise deriving from this power level will not be a problem if we can reach a positional stability of the components of 3.8 nanometer per square hertz, and this will not be a problem to reach. So the conclusion is that from the stray light point of view, the adoption of the new concept will not create problems. With that I concluded. Thank you for listening.